So let's dive into Mann-Whitney-U test now. So what does it do? Again, there are multiple names for it. One name is Mann-Whitney-U. The other name is Mann-Whitney-Wilcoxon test. It's also called as rank sum test. Okay. Again, this is very, very popular, very, very widely used. What it tells you is this. Imagine if you have two random variables, one random variable corresponding to control, one to treatment. It is basically trying to say are these distributions the same or not? It doesn't talk about greater than or less than. All that it's trying to say here is, are these distributions same or not? Very simple question. Okay, that's what it's trying to answer. But remember, it's not looking at a statistic. As in, it's not looking at, let me be careful here, it's not looking at the median of XC and the median of XT. It's not looking at them. Like all hypothesis tests, there is a test statistic here, but it's not looking at a statistic like a median of the control and treatment. That's the fun part of Mann-Whitney-U. Again, this is very popular because this is also a non-parametric test. It doesn't make any assumptions, except for some very basic stuff. It doesn't make any assumptions about XC and XT. They can come from any distribution, and Mann-Whitney-U still works reasonably well. Okay. So let's look at a couple of simple assumptions. Okay. What it says here is that XC and XT are observation. They are observations in XC and XT, which is XCIs and XTJs. Right? We have N observations here and M observations here. They have to be independent of each other. Simple, very simple, standard, basic statistical assumption. And here comes the slightly tricky part, which is all your XCIs, right, whatever you're measuring, and XTIs, they have to be ordinal. Ordinal means you should be able to order them, which means you should be able to compare if something is less than other thing, if something is equal to other thing, if something is greater than. This is important. They have to be ordinal, which means you should be able to compare them. Like numbers you can compare, but imagine instead of numbers you have countries. How do you compare countries? In such a situation, if these random variables XC and XT take the values of countries, right, then it won't work. It has to be ordinal or numerical in nature so that we can compare them. That's super duper important. Okay, so like any statistical test, we should always first ask, what is the null hypothesis, boss? The null hypothesis here is that XC and XT are the same distribution. That's the null hypothesis. The alternative hypothesis is that XC and XT are not the same distribution. In any hypothesis test, first ask yourself these questions. What is this test? What is it exactly trying to do? What are the underlying assumptions? Okay, and what is the null hypothesis? What is the alternative hypothesis? Then, once you have that, then we'll come with test statistic. What is a test statistic? This is probably the most important part of Mann-Whitney-U, because once you understand this, everything will fall in place. Mann-Whitney-U says, suppose we have M observations of XT. Look at this. XT is all the observations from the treatment. XC are all the observations from control. So it's saying, let's take, again, this is a double summation. So it's saying sum over all i's and all j's. So when you write it into code, you'll say for each I and for each j. This is like a twin loop when you write code. For each I and j, compute this function. This is a function between every pair of value in the control and the treatment. I'll show you a simple example. Okay, let me show you an example. Suppose imagine you have XC values. Let's assume these three are XC values, these three are XT values. Let's just say what it's doing here is it's comparing 1 with 1, it's comparing 1 with 6, 1 with 9. Then it will compare 6 with 1, 6 with 6, 6 with 9. It's going to compare 9 with 1, 9 with 6, 9 with 9. So it's doing like an exhaustive comparison of every value that XC takes and every observed value from XT. So compare every pair of values. That's the idea here. Okay, I'll show you how this works with a bunch of examples. So it's saying across every pair of values from the control and treatment, compute this function. Now, what does this function do? This function basically says that if the control value xci, if it is greater than the treatment value, return a value of 1. If both of them are equal, return a value of half. If the control value is less than the treatment value, return a value of 0. Very simple. Now you might say, what the heck is happening here? I agree with you that you said, hey, we're going to compare the whole distribution. Again, how did these distributions come? These distributions came from the actual observations of xc and actual observations of xt. So by comparing every value in xc to every value in xt, literally every observed value, you're comparing the whole distribution itself. Okay, now while this formulation looks simple, getting the intuition is the key. Now let's try to get the intuition, right? So the intuition works as follows. Suppose these are the 3 values that I got from control. These are 3 values that I got from treatment. Okay, let's compute the status. Again, this test is also called Mann-Whitney-U because the test statistic is often referred to as U, often referred to. Right? So let's go step by step. Now let's understand how this test statistic itself works. If xc is same as xt, exactly same values, what happens to u? Okay, first you will compare 1 with 1, same value, so you give it a value of half. That's what your function s said, right? What did s say? S said, this function s is basically saying, if the control is greater than treatment, give 1. If they are same, half. If control is less than treatment, 0. Simple. Okay, first we are comparing 1 with 1, same, that's why half. 1 with 6, control is less than treatment, so 0. Control is less than treatment, so 0. Okay, done. These 3 values are done. Again, it's a summation, right? Then this versus this. Control is larger than treatment, so 1. Control is equal to treatment, half. Control is less than treatment, so 0. Same logic, same. Control is greater than this, so 1. Control is greater than treatment, so 1. Control is same as treatment, half. You sum up all of this. Again, because these values and these values are exactly the same, look at it. How many values will you get? Look at this. You got a half here. If you think of this as a matrix, right? Half, half, half. This is 1, this is 1, this is 1. Or rest everything will be 0. So the values that you'll get here is 1 plus 1 plus 1, which is 3. And in the you can think of this as a matrix, right? If you think of this as a matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. Because these values are exactly the same. The lower triangular matrix, these values are 1. The diagonal are half. The upper triangular is 0. So the actual value that you'll get is 4.5. And you can easily show that if you have n values here and m values here, and if the distribution is exactly the same, perfectly the same distribution, then the test statistic u that you will get is m into n by 2. Logical. Again, you can easily argue that because when you're comparing this with this with this, you're going to get halves, right? When you're going to compare this with everything else, it's going to be less. This, half of them will be greater, half of them will be less. This, it's going to be greater than all others. So you can test this. Instead of 3 values, take 5 values. You can do this simple tabulation. So the U statistic, if you think about it logically, if you think very logically, what the U statistic is saying here is, if the control and treatment values are the same, give it a value of half, or else give it an extreme value of 1 or 0. Okay. So now here comes the beauty of this test. Again, I'm hats off to these people, Mann, Whitney, and Wilcoxon, who discovered this. This is a phenomenal idea. Okay, so they said, okay, this is all cool. Now let's take a slightly different example, right? Again, here also we have m equals to 3, n equals to 3. But if you see, let's assume these two distributions are not the same. This has 1, 6, 9, this has 2, 12, 18. So if you just even see that these values, xt is a much larger distribution in terms of values, right? xt is going to be here xc is going to be somewhere here. Again, I just made that up, right? So they're surely not same. Now, when I compute the U statistic, what happens to this? Okay, so 1 compared with 2, 1 is less, so 0. 1 is less than 12, 1 is less than 18, so all 3 zeros. What about 6? 6 is greater, so you got 1. 6 is less, so you got zeros. Similarly, 9 is greater than 2. So you got this, rest everything will be 0. So you got a value of 2. I'm just showing you how to compute the test statistic here. Similarly, what if you have this? Here also both of them are different. Remember, both of them are different. But here xt as a distribution is less than xc, right? Because these values are smaller, these values are typically larger. Again, if you compute this, the u value that you're going to get is large. Look at this. How is your u value behaving? Just let simple examples we can use or we can employ to understand this. The way this u statistic is designed is this u statistic, if both the distributions are the same, the u statistic that I'll get is going to be m into n by 2. If this xt's distribution is larger than xc, then I'm going to get a value that is less than m into n by 2. On the other hand, if xc is greater than xt, I'm going to get a value larger than m into n by 2. Okay, simple idea. Now, okay, so all that is cool. So literally the most fun part here is, again, I don't know how these people even invented this. This is like phenomenal. Of course, there is a very rigorous mathematical proof that you can learn at graduate level on how this was derived in the first place. But the idea here that they came up is this. If again, remember, your n and m, which is the size of your control and treatment, if they are reasonably sized, greater than equal to 20 elements, then under null hypothesis, your u is going to be normally distributed. This is very important. Remember, till now, what have we done? Let me just quickly recap so that you have everything in context. We said, okay, these are the assumptions under which Mann-Whitney-U will work. And what we did was we said the null hypothesis is the control and treatment are same. Alternative hypothesis is they're different. Then there is a specialized metric that is defined. And this metric is defined as follows, where we are taking every pair of values from control and treatment and doing a simple computation. And the idea behind it is when both the distributions are same, you're going to get a value of m into n by 2. When one distribution changes from the other distribution, you're going to get a value which is either less than m into n or greater than m into n, significantly. Now, here is one of the great ideas. If m and n are greater than 20, under null hypothesis, what is our null hypothesis? That xc is same as xt. Under null hypothesis, as long as the sample sizes are large enough, if the null hypothesis is true, then u is normally distributed, Gaussian distributed with some mean and variance. This mean is exactly this. Again, this is again, remember, our null hypothesis is that xc and xt have the same distribution, and the standard deviation of this of u is going to be this. Now, look at this. This is very important. Now we know the distribution of u. We know that u is going to be normally distributed with some mean and some standard deviation under null hypothesis. We know this. And then we have an observed u. Let's not forget that. If null hypothesis were true, under null hypothesis, we know how u behaves. We know the distribution of u. Okay, we know that u behaves like this. U has this sort of distribution. Okay, if under null hypothesis, I know that u will have this distribution with this mu and some with this mu and some standard deviation. Now I'll take the observed u from my actual setup. If this observed u is extreme valued, suppose let's assume this observed u falls here. Let's assume this observed u falls here, or if this observed u falls here, then look at this. Okay, so let me draw this curve better. So let's assume I have this. Okay, let's assume I have this. Then if this observed u falls here, let's assume your observed u. Okay, you know how to compute, right? Given xc and xt, we can compute it using the double summation. Then I know that this, because the fun part here is I know the underlying distribution of u as long as n and m are greater than equal to 20. I already know this. This is one of the fundamental contributions of Mann-Whitney-U. So if this is my observed view, I know that this is Gaussian distribution. I know the exact mathematical formula for the PDF. And I can exactly tell you what is the area under this curve, right? So then using this area under the curve, I can get the p-value without having to do any permutation or anything. Similarly, if my observed u is this, if on the other hand, it could be other side also, right? If this is your observed view, what is the possibility that this value is this small? Because we know that if the null hypothesis were true, then you would have this distribution with the mean, also the mode and the median at this value, mu u, right? Mu u itself is m into n by 2. So here, I don't have to do any resampling or anything. That's the fun part. This is the most important part. This is much more cheaper to compute. No resampling, no headache, no permutation, nothing. All I'm saying here is, boss, I have m observations. I have m observations from my treatment, n observations from my control. I'm just computing this metric. And as long as n and m are greater than or equal to 20, I know under null hypothesis that u has to follow the normal distribution with these parameters. And I have formulae for these also. I already have the formula for it. Right? I already have, I mean, that's the core research work that Mann-Whitney and Wilcoxon did. Now, how do I do my hypothesis test now? Very simple. My null again, let's go back to the drawing table, right? This is my null hypothesis. My null hypothesis is xc is same as xt. My alternative hypothesis is this. I will compute the observed u. Some observed view I'll compute. Now, given that I have the observed view, all I have to simply say is, given that u is normally distributed and this is my observed u, I just have to compute this area. And if this area is, let's say, 2%, again, I'm just making it up. Okay, if this area is 2%, then I can, again, if my significance level is 5%, I will reject the null hypothesis. When I reject the null hypothesis, I accept the alternating hypothesis or the alternative hypothesis, which says that xc is not same as xt. That's it. Very simple. And that makes logical sense, right? Look at this. Again, let me give you the intuition, which is the most important part. When the distributions are the same, when these two distributions are same, most likely what you'll observe here is a value very close to the mean. As these distributions differ more and more, the value that you'll observe of the U statistic is going to go farther and farther away from the mean here. I just took this simple example to drive that point, that if xc and xt have the same distribution, what you'll see for the U statistic is same as the mean value. But as the distributions go farther and farther away, this value will go farther and farther away, either in the positive direction or in the negative direction. So in this case, we are going away from 4.5 in the negative direction. In this case, we are going in the positive direction. Whichever way we go, we are going away from the mean behavior. So if my observed view is extreme either in this direction or in this direction, doesn't matter. As long as it is extreme, as long as it is not in the central behavior, as long as it's not behaving the way it should behave under null hypothesis, I will reject the null hypothesis. Simple. Same concept, nothing fancy, very easy to understand. Okay. Now, remember, there's a fundamental difference between Mann-Whitney-U and our permutation testing or permutation resampling test. In the case of Mann-Whitney-U, we know the distribution of the test statistic when n and m are reasonably sized. When n and m are greater than 20, we know that u follows a Gaussian distribution with a very clear mean, which we can easily compute, and a standard deviation. So because of this, what happens? Computing this p-value, computing the probability that the test statistic is greater than the observed value under null hypothesis is very simple, because it's all about finding the area under the Gaussian distribution. It's too simple, right? Okay, cool. Now the second part here is, in the case of permutation testing, we don't have the distribution of the test statistic. Imagine if my test statistic is the median difference. Okay, if my test statistic is the median difference, I don't have the distribution of the median difference. I don't have it. I have to obtain the distribution of median difference through simulations and resamplings under the null hypothesis. I don't have it. That's why permutation testing is slightly more cumbersome because of the computational overhead than Mann-Whitney-U. So that's why Mann-Whitney-U is also more widely used. Why is it more widely used? Because it is simpler computationally. And it is comparing whole distributions. If you have two distributions like this, it's comparing literally, it's basically saying, are these two distributions same or not under some basic assumptions. It's completely non-parametric. You might say, hey, why is it non-parametric? You're saying that U follows normal distribution. Yes, I agree with you. The test statistic follows normal distribution, but your observations XC and XT need not follow any distribution. Again, remember, it's not saying that XC and XT should follow a specific distribution or some properties of XC and XT should follow a distribution like the T test or the Z test. Saying, give me any distribution, give me any data, as long as the observations are independent, as long as I can compare these values, as long as they're ordinal, as long as I can compare greater than, less than, equal to, I will do it. The fact that U has a normal distribution does not make Mann-Whitney-U parametric, because it's not making any assumptions about the random variables that we're comparing. And the most beautiful part is every pair of values is compared. But there are also drawbacks. It can't, again, the test itself is not designed to say whether XC is greater than XT or XT is greater than XC. All that it says here is that the null hypothesis is XC is same as XT, and the alternating hypothesis is that XC is not same as XT. That's all. It doesn't talk about greater than or less than or anything. But again, there is something called as two-tailed tests and one-tailed tests, etc. Right? So the idea behind two-tailed test and one-tailed test is, again, there are variations. What I'm giving you the intuition of is the most basic form of Mann-Whitney. Okay, so one-tailed test basically means you're computing how much area is there in one side of the tail. A two-tailed test, you can say, is when you say, hey, I observed a value as extreme as this. How much weight or how much density is there on both sides? In this case, we don't have to use that. We can just use one side, and it will work reasonably well. There are tons of variations of what we're discussing, but the fundamental idea is to drive the point on Mann-Whitney-U. Again, lot of statistical tests follow the same rule book. Okay, let me recap the rule book quickly for you. The rule book is this. The test basically says what it's going to compute. Okay, it clearly says what are the assumptions under which it will work. You have to be very careful about this, because if these assumptions don't hold, your whole test goes for a toss. That's one of the reasons why some hypothesis testing can go wrong. What is the null hypothesis? What is the alternating hypothesis? What is the test statistic? And for this test statistic, do I know a distribution under some reasonable assumptions? If n and m are reasonably large, I know that the test statistic follows this distribution. If the moment somebody tells me this, I can compute this whole area very, very easily, right? So that's the idea here. Okay, cool. Now let's move on. Okay, now I have a question for you. Okay, so let's go a little interactive now. What is the maximum value of the test statistic U, and when does that occur? Think about it. Okay, let me show the formula for you. Okay, so the question here is, what is the max value of U, and when does that occur? What is the maximum value? Okay, and when does that occur? Very simple. This is like literally 5 seconds question. We're not talking about the mean value. What is the maximum value of U? I think some of you are confused or you are sleepy. Okay. I think some of you got it, some of you are a little confused with it, right? So it's actually very simple. Think about this, right? If you have xc and xt, if all the values of xc are greater than values in xt, simple, just simple example like this, right? So this is greater than this, so you get 1. This is greater than this is greater than this. So if xc, if every value of xc is greater than every value of xt, okay, this is okay for every value, for all ij, for all I and j, if xci is greater than xtj, then you'll get all ones. How many ones will you get? Because you're doing, if there are n values here and m values here, you'll get m into n. Very simple.